We are very excited to be your last panel of the day. It's been a really fun day listening and getting excited about what has been done and what's about to happen. And today, this panel gets to lead into the Tech Showcase, which hopefully fosters a bunch of conversations about lessons learned and opportunities to connect. So today, we're going to kind of walk down and highlight some Tech Showcase, and then we'll go out and get to see even more. Much like the last panel, if you have specific questions, we're probably not going to ask for the individuals. I will encourage you to go talk to them at Tech Showcase, but we'll talk about some more general things and just get excited about getting to see all this great technology and all the things that await us outside. So let's get started.
Hi, everyone. I'm Dean Bergman. I'm the Director of Business Development at Honeybee Robotics, a Blue Origin company. So you've seen us around a lot, especially over the last couple of days. We really do everything these days. So you saw some of our drills, some of our stuff that was on the moon, some of our sample handling. We're working on the landers and whatnot. We're flying another rover with Firefly in 2028, and we do have payload space on that, so come and talk to us if you want to fly along with us. But like I do every LSIC, I am here to talk about our power tower, or LAMPS, our Lunar vertical solar array. Let's just get started. So what it is, it's a 20-meter tall, 10-kilowatt tower, very similar to what Steve was talking about in the last panel. We were selected under GCD, the Lunar Vertical Solar Array Technology call from NASA, to build and test our tower up to TRL-6 in JSC's Chamber A, which I have some video, so we'll get to see it in a little bit. But it's made out of our Diablo deployment mechanism. We actually have a small version here out on the floor, so come by and play with it. It's pretty cool. There's also dust-tolerant connectors to connect to the tower, also here on the floor, and you can also touch and play with those. And then we also have a lot of flight heritage in our avionics, which is now flight-proven on the moon, which is pretty cool. And then we're working alongside a company named mPower for flexible solar arrays. So this is it. We did it. We did the thing. We did TRL-6 in Chamber A. So that's it going into the chamber and then fully deployed at ambient. To give you a sense of how big it is, you have the little astronaut next to it. You don't, you always look at these things and they're like 15 inches, right, on your screen. You don't get a sense of how really huge this thing is until you see it. It's mind-blowingly big. The other pictures I have of real people with the hardware, they're all pretty far in front of it, so they fit in the screen, so you still can't get a sense of how big it is. But I was talking to Wes earlier, and we were both saying these things are huge. It's crazy. But we did full deployment at ambient. We did cold. We did a little bit of hot. And then hopefully next up is the moon. So instead of me talking, let's see how it works. So the way it works is that Diablo extends and puts the arrays to a 20-meter height, and then the arms deploy, and then we deploy a blanket of solar arrays down. Now, these were not populated with solar cells, but the carriages that hold them are the equivalent mass of what they would be on the moon, so it was a pretty good mass equivalent test. We did have a gravity offload system for the boom itself, but that was more for safety reasons. The Diablo can actually deploy in Earth's gravity too. And then this is at cold, so it's the same, but in cold, and you can really tell the difference. So this is it going out again and deploying. So we had a very successful test at ambient and at cold. And then we can, for this one, we did each panel individually. We can do either deploy them all at once or individually. And then with the hot test, we only did a partial deployment. The cage around the system is the heater cage. To do a proper hot test, we would need a heater cage that filled the entire chamber, which would be extremely expensive. So we only did a partial heater chamber, which meant that we only needed to prove that, after heating, it would deploy past the chamber, and so we did that one too. Looking at what's next for this in terms of, power architectures and infrastructure on the moon, we've worked with DARPA and, other companies and other institutions to look at next steps. So it's a very scalable system. So what you see here is, for the picture on the right, the top right corner, lamps is the little thing at the bottom, and that's already 20 meters. And then, Statue of Liberty, and then our 100-meter version, and then a 200-meter version. So the idea of that is not only creating power, but also putting payloads at a tall height, PNT, comms, laser beaming, power beaming, whatever you might want. And then you can also, at perpendicular to the power, you can add radiators and create what we call Lunar Oasis, which is both power and thermal as a service. So you can both drive up to it, charge, dump power, or get power to dump heat or get heat to survive the night. So it kind of works both ways. And then, next steps are getting it on the moon. So I think the first shot would be, making a node with Mach 1, like you heard from Jackie earlier, put a tower on top and just deploy it off of that, and then you've got your first power node on the moon. The current system was designed to be deployed up to 10 times, so that would probably be the next step, where you have it on a mobile base, where you have a rover go place it, drive around for a year, it will stow, drive it to another location, deploy it for another year, and do that for 10 years. And then, eventually we want to create a power grid on the moon so that everyone can utilize it. But yeah, that's it from me. Thank you.
Hi, I'm Tim Mounsey. I'm the Director of BD at Lunar Outpost, and just want to thank the LSIC organizers for putting this on and giving us the opportunity to talk a little bit about MAPP. We're very proud of MAPP, our mobile autonomous prospecting platform. And just, a little bit of background, we, I think as many of us here, see robotics as the trailblazers of the new frontier, the workforce of the future. Astronauts are not necessarily going to be swinging hammers and deploying infrastructure on the lunar surface. It'll be robotic systems that are doing that efficiently, going to places and environments where humans cannot, and ultimately paving the way for a permanent lunar presence with the deployment, operation, servicing, and commissioning of infrastructure. Which brings us to MAPP. So this is our Explorer class rover that we developed. It's a third iteration of this particular design, and it has heritage. It's been to the moon, which I'll touch on a little bit later, but it was designed to carry technology payloads, both science and commercial, in various configurations, as you can see in the top right, both external and internal mount. And really, just given we're still in this mode where launch costs are a huge factor for getting things to the moon. So our team really wanted to emphasize the ratio of rover mass to payload mass. So you're looking at a 15-kilogram rover with an up to 15-kilogram payload mass. So really trying to trim mass wherever we could. So the suspension, the topology, designed wheels, all designed to have a lower rover mass so we can optimize ROI for our customer payloads on board, but a really flexible system that is really designed to be a rideshare payload on CLPS landers. And talking about lunar mission flexibility, We've thought about we're operating on the poles, operating at mid-latitudes, operating on the far side. What does that mean? We have configurations, as you can see here, from a power generation perspective, where depending on where the sun's angle is, depending on where we're operating, we can make sure we're perpendicular and getting and generating power from the sun. So that first mission was a South Pole mission, so we had our panels on the sides of the rover. And then on our second mission, which would be more of an equatorial region, we're going to be flipping up, during lunar noon, so we can capture the sunlight and continue to power. But also, thermal is a consideration for these different locations. And we have a thermal switch on board that was developed by our European colleagues in Luxembourg. That changes the conductance of thermal for our system, so we can dissipate heat, we can retain heat depending on the operations to keep a nominal thermal state for the rover itself. And as I mentioned, we've landed MAPP on the moon. It was on the IM-2 mission, so it is up on the moon today. And we have regular lunar missions that are going through the end of the decade. I'll talk about our Lunar Voyage 2 with APL. And then we have a commercial mission in 26, and then also building the lessons learned from these MAPP missions will help us build the Rover platform for the Australian Space Agency for their first lunar mission in the history of that nation. So Lunar Voyage 1, this was to Mons Bhutan, again on the IM-2 mission. It was carrying several payloads on this mission, primarily supporting Nokia's 4G communications network. It was going to act as a node for that network, hence the antennas that are deployed from the rover, as you can see on the photo. And ultimately, we were going to drive out line of sight to test the range and strength of the comms for Nokia. But also some fun ones on here as well. MIT had 3 payloads on board. One was a micro rover called Astroant that was a 50-gram rover that was on the top of our rover, would deploy out of a tiny garage and would take radiator readings from our rover as it operated. And they also had a resource camera on board and a humans disk that had messages from around the world in all different languages. And some fun ones there as well with non-space companies, trying to get them involved, trying to get, broaden the audience for space exploration with Adidas and Juventus. They put a little decal on the rover. And I also, too, that I didn't put on here, that's my fault. The Pulley Lunar Snooper spectrometer was on board here as well as Lunar Crush's Nakamoto 1 crypto treasure hunt. So there is a private crypto key on the rover. I think there's like $400,000 worth of Bitcoin on it. So maybe in the future it's worth millions, maybe nothing. So I'm looking forward to the space pirates that get that key in the future. This is just a photo of MAPP and integration on the Athena lander, and just some metrics or sort of highlights from that mission. MAPP, although there was an off-nominal landing, MAPP survived. All the data that we received back indicated that MAPP survived and would have been able to deploy, which is great. And ultimately, a number of our key subsystems went to TRL-9 for this mission. So a lot of data back, over 6 million data points. We've sent 312 commands to the rover during its time, both in transit, in orbit, and on the surface. So a lot of great data back that we're using to continue the progress of our future missions. And just some operational milestones. MAPP spent 132 hours in lunar transit, 77 hours in orbit, and then operated for 2.7 hours in a shadowed crater on the surface at negative 65 degrees Celsius. So, really proud of what we were able to do, just given the circumstances of the mission. Which brings us to our next mission, which is Lunar Voyage 2, where we're going to Reiner Gamma, partnering with the folks at APL to deliver and host their Lunar Vertex payloads. So a magnetometer and a multispectral microscope to really explore the magnetic anomaly that is Reiner Gamma, measuring the structure and strength of the local magnetic fields that are believed to create the magnetic swirls on that particular region of the moon. So really excited to be working with APL on this mission. And I would just say that all of these missions, these MAPP missions over the next couple of years, gives us great experience, great data, allows us to increase the efficacy of our subsystems, and all leading to these larger mobility platforms that we're building, like LTV, which is pictured here, which will launch in 2029 with Starship. So if you have payloads that require mobility on the lunar surface, come talk to me. Would love to see how we can work together.
Hello everyone, I'm Carter Waggoner. I'd like to take a moment to thank everyone for the opportunity to speak here. Today I'll be representing Aerofly LLC. We are an engineering startup company. We actually got our start from a NASA drone contract. And we're also closely partnered with South Dakota State University. And I would like to tell a story on kind of why we're here today. So as seen up there in the top left, you can see the NASA Break the Ice Challenge. It was a Centennial NASA Challenge. And in this challenge, our team kind of learned a trick to convey lunar Regolith vertically. So we are an engineering startup, so this was our first round of applying for some phase 1 SBIRs. So we put in for 3, and we luckily got this first the opportunity to complete this first phase 1 SBIR, and we had the pleasure of working with Robert Mueller. So I just want to lay out some of the requirements that we had during this SBIR. So per the solicitation, we had to deliver lunar Regolith 10 meters tall in height elevation at a rate of 10 kilograms per hour. And then we also had to ensure 1 year of continuous operation. And we also had to make sure that our system was capable of interfacing with adjacent systems. So our Rego-LIFT system, which stands for Regolith Lunar ISRU Feedstock Transporter, utilizes this very unique mechanism called the static screw conveyor. Now, the static screw conveyor consists of a simple static auger that does not move at all, and then the driving mechanism comes from the outside drum with inlet feed scoops. We have a fantastic tabletop model. We invite everyone to come to our tech demo table and give it a spin so you can get a better understanding of the mechanism. So to start off, we wanted to conduct a state-of-the-art for our phase 1 and kind of learn all that we could. And what our kind of mechanism offers is some benefits when it's a purely volumetric feeder. So compared to traditional screw conveyors, we can get superior flow rates in smaller form factors. And it's also a very simple mechanism, so it can be more reliable than some chain-based mechanisms that have higher chances of failure. So to kind of lay out what we accomplished in our phase 1, we had our state-of-the-art review. We had a test bench that we used LSP2 Lunar Simulant, and then alongside of that, we created a DM predictive model, which was a digital twin to match that experimental data. And then to ensure the feasibility of 1 year of continuous operation, we had a reliability analysis. So as can be seen on screen is our TRL4 experimental test bench. Per some recommendations from our point of contact, we use Lunar Simulant to kind of prove the feasibility of our system. This was a 1.5 meter long test bench module section that we could run experiments, get some data for our incoming predictive models. So also from our suggestion from our point of contact, our simulation team used Project Chrono open source DEM to create a digital twin of the experimental test bench model so that we could take that data and match it and create a new model so that we can help for future designs. So here's one example of a use case, but our system is flexible, scalable, and open to various other use cases anytime material handling is needed. So as can be seen on screen, you can see the IPEX excavation rover delivering some Regolith payload to a hopper size sorter system. The size sorter then delivers the Regolith to our Regolith modules that can be used in series and transfer material from one module to another. And then as you can see, our Rego-LIFT system is attached near a lander and can then deliver the processed Rego-LIFT for further processing. One key takeaway that we learned in our Phase 1 SBIR is that we are able to get experimental data and then use our DM model to match that data so that we could create predictive models for the future. And also, our system is extremely scalable, so if a customer would need a certain flow rate at a specific RPM, we could scale our system to match their needs. Pending Phase 2, here's the future work plans. So we have been looking into a 10-meter tall multiple module prototype that would be on terrestrial, under terrestrial environments with a simulant. This is just to prove 2 weeks of durability. And then also pending Phase 2, we would be exploring vacuum chamber options and exploring a partnership with Honeybee Robotics to get a chance to work with their vacuum chambers and get their guidance on the topic. And then outside of the SBIR process, we have just recently applied for TechLeap prize to get a chance to get a vacuum model and also operate our mechanism in low G so we can see the effects of low G. As preliminary results show that under low G, it would be even easier and it would require less power to drive our system. And then here can be seen an example render of what we would kind of like to do for TechLeap. As of last week, our team is extremely happy that we have been selected for Phase 2 contract negotiation, and we'll be pursuing this, and we are super happy. Would like to take a moment for some acknowledgments. We'd like to thank our partner, South Dakota State University, for all the help along the way, and also for the great opportunity to work with the great people we met at NASA, our point of contact, Rob Moeller, and we also had the great benefit of working with Jacob Collins as kind of our ISRU industry advisor. Here's our contact information. I invite you to scan the QR code. It'll take you straight to our website, and we'd love to hear from you for any collaboration or offer any possible engineering services. Thank you for your time.
Good afternoon. My name is Jeff Buell. I'm the Program Operations Manager for Commercial Space Services for Aegis Aerospace. I'll be talking about our lunar payloads that we currently have already on the moon, and actually we have 2 more payloads going on to the moon here in the near future. Whoops, how did I fill that out? All right. So Aegis Aerospace, just real quick, we already went over this yesterday. Aegis has a heritage of over past 30 years of working in the DoD and the NASA community. Our hardware that we flew to the moon actually related to our experience working on the Missy Flight Facility on the ISS. And just examples of what we have flown or operated and currently flown before. Missy FF is right now on the ISS. It's external payload, which it's been on the platform for over 70 years. We also have a small M1 bus that we have flown off the ISS. And now we actually have 1 lunar payload right now that's on Firefly, thank you, getting us to get the lunar surface, and that's Rack 1, and we have Step 1, which will be heading off to with IM3 early next year. So that's just a little more information about our rack and our staff. These actually, 2 of these demos will be actually at our table, so please drop by. And I'm going to get a little more about rack here. Our rack platform. I want to get a little more about how we got integrations to operations and on surface operations. Rack was a request of service proposal. We won that through Marshall, and started in 2020. Over time, we actually started working with Firefly, got part of the 19D contract, CLIPS contract, and we got on board with Firefly. During that time with Firefly, we had a great working relationship with them in the CLIPS office. They were anything we had any issues, they worked with us, especially as the payload manager and also the operator. They were hand in hand of any issues we had with the lander, integration for the lander and our payload, and pretty much pretty flawlessly for our 2-year period. We had some issues, but we were able to work all that out and get us going. So, on the way to the moon, this is the pictures from Firefly themselves. Thank you again, Firefly. So on the way to the moon, we actually, during our transit, we did several state of healths once per week. One of the things we did learn during on the way to the moon is that redundancy computers is awesome. We did have one time when our primary computer did not want to boot up properly during our state of health. Our secondary took over and did what it needed to do to make sure our diagnostics, just to verify everything's working properly. Powered down for another week, then finally our primary computer booped up again as planned. So redundancy is something I'm really a big fan of. That's something we have done on our platform on the ISS. We finally landed on the moon. We spent the good old 14 days there on the moon. Again, this photos from Firefly you've seen probably out there. So during the time on the moon, we're able to do surface ops early. We're supposed to do our first photo ops with RAC of our samples. Again, RAC was, I apologize, I realized I just skipped over that, is that RAC had 15 samples of materials to take photos of. That was our mission, was to actually see how Regolith would actually interact with the materials. Once we landed, 5 hours of landing, we actually started taking photos of the samples. We did that for 2 days, then things got a little hot for us, and we had to turn off our payload to make sure that we get through that thermal conditions. So we kind of chilled out for a while, then finally get turned on back on 10 days later and started taking photos again. Even though we went through that thermal conditions, we have no issues getting our rack back on, start doing like it was nothing. We tested that. That's one of the things we did learn. We knew when the temperatures, when it hit a certain point, our computers were starting out processing certain packets. So we saw that during our data before we turned off. So it kind of related to the testing we did on ground, actually reflected on the surface of the moon. So we were able to do all these photos, able to download those photos, and eventually turn off our rack on the 14th March. Of the samples we actually sent them to our customers or experimenters. So we actually had 15 samples. 6 of the customers were from NASA research centers, and 4 of them were from commercial entities. And so they're able to get the photos, start doing their analysis of what the materials is and what type of Regolith came on. And here's a sample of one of the slots of the 15 samples, and this is actually something we learned too as a payload provider. Testing, when we tested these samples over, we only did it in a light area, direct light looking down on it, or actually turn off the lights. As you can see here, as the days progress, the sun angle has changed and the imaging has changed as we dealt with that. Second thing was the biggest kind of cool things that we did land on 2 March. We had nothing on that sample. Then LPV and EDS did their experiments under us, and we actually got some dust. As you see here, we actually turned off, and on 13 March, there's no more dust. So it's kind of interesting. We're trying to scratch our heads why that happened. So science has happened. We're happy to see some dust. We were puzzled why we didn't have dust in the beginning. We got dust after LPV and EDS experiments. Then it went away after 10 days. So that's something we got to figure out why that happened. And that's what the researchers from NASA research centers and the commercial customers will figure that out for us. So that's kind of why we're doing this, is understand how this material reacts to this Regolith. And that's going to help us out down in the near future for all the different things from the rovers and everything you're all doing here. One of the cool things also here is actually we got a reflection of one of the samples and actually saw the surface of the moon at one of the samples. So that was kind of cool. So I can say RAC actually took photos of the surface of the moon now. So I can put that in our great things we did for RAC. Also, we have our next platform called STEF. It will be able to have 6 different type of experiments. That includes material science. We're testing out solar cells. We'll be testing for a customer, 6 different customers. We'll be testing out a radiation sensor and some other type of components for computers. And that's what, this was a tipping point by NASA. And we'll plan on flying this one on IM-3, and we'll actually be flying this in the near future. We're already starting to work at STEF 2 on a future mission here in 2 or 3 years from now. And I believe that's it in a nutshell. Please come by, talk about anything about operational integrations. probably give you ideas how that went through our process over the 5 years getting rack ready for getting to the lunar surface. Thank you for your time.
Great. Thank you all for sharing, and lots of good lessons learned and throughout the process. I know you're all kind of at various stages of development and thinking about a broader lunar ecosystem. Can you tell us something that you wish you had known at the beginning that you now know that might be helpful for the crowd here?
Okay. When we started this, we were kind of hoping and we were under the expectations that there would be, this pathway to multiple rounds or multiple phases to eventually get this on the moon. With current climate and, politics in general and just different priorities, if we kind of had known that there wouldn't be a next phase after this, that there might be a bigger gap between getting to TRL-6 and then trying to get this ready for flight. We might have tried to prepare things earlier or kind of do a couple things differently to kind of push our agenda a little bit to get this on the moon. But yeah, besides that, I think everything else went pretty well, so I can't really complain.
Yeah, I think something I'll comment that maybe is just a lesson learned is that we went ahead and started prototyping immediately on this system. And talking to our founders of the company, we had real hardware built that we could show folks that was operational, that when we said, hey, we can provide these services on the moon, we could actually show the hardware that we were ultimately building to do that. So I think that's just a testament to sort of build an MVP, right? Like these are essentially, if you think about the Explorer class rovers, they're MVPs for mobility service that will ultimately, lead us to building a much more capable system. And I think that's just a sort of lesson learned, be nimble, use other people's money from a capital standpoint and build something that ultimately can provide value now and that will set you up for the future.
I guess we were a really young team, so this was our first SBIR in general, so just getting the chance to complete one, getting the understanding of the process will kind of help us better organize for the future.
I think for us is really working with our customers that have to go through that process. You all have. So our system was lucky we had that legacy knowledge already to get us to where we're at for rack and stuff. Trying to help our customers get those funding to fly on us. That's really kind of the challenge for us to get the next, like Steph is a good example, is like different partners will be on there and they have to find the funding to fly with us too, because it's not cheap to get to the moon. We have the hardware ready to go. We just need to find the people to have the money to the SBIR process or the type of funding to get on board and get us going.
Yeah, great. How you all have kind of mentioned, different, maybe working with different companies or collaborating. How do you think about cooperation and collaboration as part of this larger lunar economy?
I mean, it's extremely important. There's no way any one company can do everything themselves, so we need to work together. I mean, there are 3 companies doing power systems, and that's not unintentional. There's a good reason for it. When we have a grid on the moon, it's not going to be a single company that monopolizes it. It's going to be multiple companies, that work together, work in unison, use these standards to provide power, provide, this infrastructure for a robust economy on the moon. So we have to collaborate.
Yeah, I think to go off that comment, there are going to be heterogeneous systems on the lunar surface. And from a mobility perspective, there will certainly be multiple rover providers. I know, obviously, you guys are building a rover. We're building some rovers as well. And but they can work together, right? There can be swarm operations. So if it's deployment of power infrastructure, power grid technology, comm systems, we can these systems that are already deployed on the surface can work together. So I think that's going to be huge just to continue the progress of the lunar economy.
After phase 2 is all set up and running, our collaboration with Honeybee will be fantastic. We'll be able to get guidance on how to set up our mechanism and get it ready for thermal vacuum, and they can let us know what shortfalls to avoid, and we'll have a better end product.
Yeah, I'm totally in agreement of we have to work together as a team, and it's the only way we can get together. As we, not only older companies have worked together, but also newer companies, newer technologies, we all have to work together and learn from each other, because you may have an idea that we haven't thought about. It's the only way we're going to get to the moon and Mars, is working as collaboration. It's not the old days of Apollo.
Yeah, and I'll just comment, I think with these larger systems that obviously we heard Jackie talk about, these larger systems that are going to be, for these very large lander systems launched before the end of the decade, which is really exciting, but ultimately going to drive down the cost to put something on the moon. And for like sub-class D missions, that are riskier, folks can really fly a sort of an MVP of a full system. And I think that's just going to really open up the possibilities of what you can deploy onto the moon.
Yeah, getting that minimal viable product and really starting to look at what does that look like over an architecture, right? Or an infrastructure. I mean, it's very exciting. This is a question kind of thinking about, and you all are at different phases of what the next step is, and we've talked about this a little bit, but what is your most important next step as you see it? Besides funding, let's take that off the table because we talked about that a couple of times, for either, do you think there's something in your systems about human interaction or really operational simplicity or maybe being part of a lunar infrastructure? What do you see as your next steps that you need to get through?
Well, besides money, for us, the next steps would be to get it flight ready. I mean, we're at TRL-6 now, and everything from now is engineering development. There's no more technology development. So while we didn't have avionics in our TRL-6 system, we have other avionics, but it still needs to, be designed specifically for this flight system. So that would be our next step, to do the power avionics and whatnot to really get this thing full flight. Because right now it's sitting as a doorstop in our lobby. So now it really is just taking the next steps and getting money and then getting ready for flight.
Just put money off the table.
Money's off the table.
Yeah, money is no object. I think we've touched on it a couple times, but it's about, I think, interoperability. When we think about a system like LTV, which is an infrastructure component that enables infrastructure deployment, from a sort of power sharing perspective, from just a sort of connection perspective, from a mechanical standpoint, a power perspective, I think having those conversations and coming to a standard, I know we probably beat this over the head a number of times, but it's super important, coming to a standard that we can all design to and that is interoperable, so then we don't get up there and when the LTV wants to share power with Honeybee's Rover, it's not like these don't mate. It's a possible thing. So I think it's about really establishing those standards so that we can design for that architecture.
I guess for our team, we're just most interested in doing the best job we can for our 10-meter tall prototype and ensuring that our vacuum model succeeds and is ready for those conditions.
For us, this is really about space testing on the lunar surface in LEO and the GEO area. But we probably need to progress beyond the testing and be part of what you're all doing. Is that something we as a company have to look at too? Is that we have continuing testing, but we also want to be a part of the lunar economy. So that's something as a company we have to not stay in that same little area. We have to expand, just like you're all different companies are expanding. Hey, we have 5 different things. And so that's something we as probably have a company look at that in the near future. But like I said, compatibility is going to be something critical on the lunar surface.
Yes, certainly. Obviously, in order to have an infrastructure system, you need, you don't want to have the railroads with different gauges, right? Another question that's been upvoted for all our panelists is, what commercial opportunities do you see for your hardware and other maybe terrestrial applications? Have you thought about that kind of interplay between space and the Earth?
I mean, commercially, it's an obvious power play. It's
Pun intended.
pun intended. Putting power on the moon is for commercial reasons, right? NASA's not going to need that much power on the moon. The idea of a grid is to make the moon commercially viable. In terms of terrestrial applications, it's a tall pole that deploys pretty quickly, so you can imagine some remote locations that you might want to put some comm systems at a height and get it down quickly for other people to not get them without saying too much. And yeah, we grew up as a drilling company, so like Wes said, everything's a drill, which is actually how this started. So we have the system itself can actually be a drill also, so we can do deep hole stuff with it too.
Yeah, so I'll probably talk to, I guess, mobility in general. I think it's an enabler, right, and for technologies, for different scientific measurement, taking whatever payload away from the landing zone and going out to a region to explore that area or test the compositional analysis of Regolith. I think, we really view our system as sort of the picks and shovels for what is possible and enabling. So I think it's whatever the good folks in this room are developing, we can help enable. And from a terrestrial standpoint, to Dean's point, I think it's about, remote environments where humans, where connectivity is an issue, and robotics can be deployed to inspect infrastructure, assist in potential search and rescue operations, go into unsafe zones like in wildfire areas to do some sort of mitigation. I think robotics have a play there.
Too soon, man.
Yeah. Sorry.
We're in Altadena, if no one knew that.
Trying to help.
Appreciate it.
I guess for our system, it really comes down to it. It's a material conveyor. So wherever there's large amounts of bulk material that needs to get moved, whether that's lunar construction or lunar ISRU, we would always be interested in providing a method for that. As far as terrestrial applications, there's always stuff on Earth that needs to be moved around and lifted. So whether that's agricultural, food industry, and a bunch of, so there's a ton of different various applications for our technology.
And for Steph and Rec, it's really about the material testing in the space environment and also giving opportunity for any type of power experiments to be on the lunar surface. Our customers the opportunity to fly there. I think for terrestrial-wise is really having that technology knowledge as they test out their materials or their experiments, like radiation sensors, or any other biological testing too they can possibly do. They can actually be transferred over to the Earth over time. And just giving that opportunity for small companies to do that.
So since we're getting into the technology showcase and we want everyone to come and talk to you guys, is there some, critical technology or maybe service or something that you're like, wow, I really want to talk to somebody about, this? Is there something that you want somebody to come and provide to you,
We have payload space on a rover that we're trying to sell. We have lots of technologies. Like I said, we do everything. So we're just always excited to talk about our technology. You'll see on our table there's four pieces of technology, all very distinct, and they're all just cool. We like to solve difficult problems, so if anyone has a difficult problem that you need solving, that's what we do. So happy to talk about anything. We just like technology. Come on by.
Yeah, not to sound like a broken record, we also have payload on our on our rover systems.
All about the money, apparently.
You got too beady guys. Yeah. I don't know what you expected.
Yeah, we're always looking for more opportunities to fly our systems, and I guess looking ahead to something like LTV, it's just going to be really capable vehicle that is not only going to be able to traverse very long very long journeys and go to places such as PSRs and operate during lunar night. It'll be able to bring a lot with it. So I can't talk about all the specifics, but yeah, if folks are developing some really interesting tech, would love to talk about how we can help you there.
I guess for our team, we'd be very interested in interacting with anyone who has an adjacent system, whether that's the hopper that receives excavated Regolith or on the MRE reactor side, just so that we can collaborate interfaces so that the system is more streamlined.
I think for us, it would be really trying if you can get your TRL level up, either in LEO or on the lunar surface, we can provide that opportunities for you. I think everyone else here wants to come by and say hello to us and see what we're doing and get us on the lander, a new next lander going up there. Pretty exciting.
I think I would also mention, like, as you know, LSIC continues and we continue to bring more folks into this community, like getting the non-space companies, you know, like the mining companies involved. You know, I think Interloon just announced a great partnership with Vermeer for an excavation or an excavator module, which is great. And I think getting those folks in the room so they can hear about what's going on, where they can, you know, get involved from a technology perspective is going to be critical. So I'm excited to, as we continue this, to get those folks involved too.
There's non-traditional folks and meetings like this where people can go and talk in the hallways as things are going on. Looking forward, and you know, I think we've talked a lot about kind of the robotic systems interacting and things like that, but we got some questions about humans in the loop. As part of this, so you know, have you been thinking about how your systems might be part of a larger human system, and what challenges do you already see as part of that, kind of looking forward ahead of just the lunar robotic infrastructure?
Well, it's a really tall tower that's 10 kilowatts, so it's not super conducive to being around humans. But it does definitely enable a human economy on the moon. You know, we'll need, yeah, you can go and fix it, sure. We need large amounts of power on the moon, and VSAT's the first step to doing that. You know, people will likely be at the poles, which is why you need the vertical style arrays. And it will just, you know, plug into a hab or charge LTVs or, you know, so there'll be some sort of interaction. When it gets to that point, robots are easier. You know, there's a lot of safety concerns that go around it when you're plugging in high voltage plugs and whatnot. So it will have to be safe for humans to be around, but definitely is designed to plug into a human architecture.
Yeah, for I talk about LTV specifically, it's a vehicle designed for the Artemis astronauts. So we've gone through the considerations on ergonomics, on usability, on capability are all designed with crew safety in mind. So we've gone through human in the loop testing at Johnson Space Center with our prototypes and gotten great feedback from the astronauts ultimately on what we need to change from a sort of controls perspective. We've had former astronauts actually interact with our prototypes at our facility in Colorado, and also had astronauts drive our prototypes as well, just to give feedback on the controls, how it feels, what they like, what they don't like, so that we can change it in the vehicle itself. But everything is done with crew safety in mind to maximize or to reduce risk and maximize or ensure the success of their mission. So yeah, we're very actively working closely with NASA to make sure that that vehicle is capable. And I think Carl Hibbets here at APL is looking at some sort of robotic human teaming as well. And I think that's just going to be, it's an area of focus for us, but it continue to be an area of focus as we have robotic systems interacting with humans and working with them or doing tasks for them. Sort of that autonomy development is something that we're looking into as well.
I guess our system's a conveyor, so we save the astronaut the trip up the ladder holding a bucket of Regolith, so that's kind of our contribution.
I can't follow that up. For us, I mean, our system's pretty small right now, but we do handle work with astronauts on the ISS. And when you start adding humans into the loop, it does cause a lot of questions because humans don't follow checklists sometimes, and you have to remind them what to do, and all that on the voice loops. But it is really have to worry about having the robotic system being very automated and astronauts in the location of definitely have to figure out how to prevent any type of collision on the surface or any type of high voltage plugging in. Something that we definitely have to do a lot of research ensuring that no damage, not only to the robotic system, but also an injury to the astronaut is going here. So it's going to take some time for us to get that. We have to learn how to do that even here on the ground first before we actually get to the moon to that. And so that's really probably the first step is trying to figure out how not to kill anyone with robots here on Earth and all that. So, sorry.
Yeah, there's definitely an added layer of complication. So what, we're here, it's been an amazing, 5 years as part of LSIC. What's something you're excited about in the next 5 years on the lunar surface? What are you dreaming about and getting you excited?
Well, I'm excited to get these 4 massive landers on the moon.
Yeah.
That's going to be hugely enabling. I mean, we can't even get a VSAT there right now. I mean, Griffin can just about do it, but once these big systems, it really opens up the capability of what you can do on the moon. I mean, getting humans is great, but the amount of robotics and infrastructure we're going to be able to put in place is astounding. It's going to be and this is when it starts. In the next couple of years, we're going to see these things starting to land, and it's going to be awesome. And hopefully, we're going to melt some regolith.
Yeah, I think in 5 years at sort of the 10-year, I guess, of LSIC.
Exactly.
I would love to see in every single presentation, folks talking about their mission on the moon. And I think to Dean's point, it's going to be enabled by these large landing systems that are able to really reduce the cost of launch and make it much more accessible for people to access the moon and companies and instrument providers to access the moon. And ultimately, I think we'll see some pretty interesting sort of infrastructure and ISRU successful missions in the next 5 years as well. So I'm excited for how that paves the way for the next 5, 10, and 20 years of creating business cases on the moon.
Yes, I don't have much to say. I'll just say my team is always very happy to check the news and see what the other companies are doing in the space. So, thank you.
I think for the next 5 years to 10 years, it's just the idea of a lander landing on the moon weekly to monthly. I think that's really the goal is to get down to get that cost point down for us to be efficient and actually able to start doing the real science in the real economy portion of the. So that's my dream. I mean, we landed on the moon. Now let's get going. All these more commercial landers and get in there and start building that infrastructure.
Awesome. Yeah, I can't wait to realize that all together. There were some specific questions. I encourage you guys to go and talk to these individuals at the Tech Showcase.
Yeah. All right. Thank you. Can we give them one more round of applause, please?